In 1269, Petrus Perennius de Mericourt used iron needles to understand the magnetic field of a spherical magnet. He was the first to discover the north and south poles of magnets. The next development in magnetic fields was made by William Gilbert of Colchester. He figured out that the Earth was in fact a huge magnet with north and south poles just like a bar magnet. The next discovery in magnetic fields was made by John Mitchell, who determined that opposite poles attract each other with an inverse square relationship. You may remember that an inverse square relationship is when the x variable is inversely related to the y variable. Michael Faraday's most famous experiment came when he wrapped two insulated iron rods with coils of conductors. He passed a current through one conductor and found that a current was momentarily induced in the second coil. This was known as mutual induction. In later experiments, Michael Faraday discovered that if he moved a magnet through a loop of wire, an electric current flowed in that wire. The current also flowed if the loop was moved over a stationary magnet. His demonstrations established that a changing magnetic field also produces an electric field. This is known as Faraday's law.
Electrons generate a magnetic field as they rotate. This magnetic field creates a pole with its north pointing upwards. Let's imagine a material in which all the electrons are spinning in random directions. Because all of the vectors cancel out, no magnetic field is created. Now let's imagine that the electrons in the material all begin spinning in the same directions. This makes all the vectors align and creates a giant magnetic field because all of the electrons are spinning in the same direction. Because all the electrons are spinning in the same direction, we can split the magnet in half and result with two similar magnets. The Earth generates a magnetic field similar to that of a bar magnet. As you can see from the field line arrows, the northern hemisphere is actually the south pole of the Earth's magnetic field. The reason why the red part of the compass is called north is because the red part of the little compass is actually the north side of that magnet, and it's attracted to the southern pole of the Earth's magnetic field. So when it's laid upon the field of the Earth, it points upward. We need to remember the magnetic field of bar magnets and horseshoe magnets. Both are similar in that the field goes out of the north and into the south pole. Let's imagine two bar magnets with opposite sides facing each other, and let's try to find the magnetic field between the two. To do this, we draw arrows out of the northern poles. Then we can draw arrows going into the southern poles. We connect these arrows to find the resulting magnetic field. Let's try doing the same thing for two bar magnets whose northern poles are facing each other. First, let's draw arrows going out of the northern poles and into the southern poles. As we draw lines connecting these arrows, make sure that the northern arrow lines avoid crossing each other. We result with this magnetic field. Magnetic fields can also be caused by current traveling through a wire. The magnetic field always travels in a circular motion around the current in a perpendicular plane to that current. Because of the perpendicular planes, let's imagine two wires coming in and out of the page. With the one on the right, we'll imagine that the wire is going into the page. So we'll draw an X as if an arrow is going in, and we'll draw a dot for the one on the left as if it's coming towards us. The magnetic field travels clockwise when facing in the direction of the current. Because of this, the one on the left will travel counterclockwise because it's coming towards us, and the one on the right will travel clockwise because it is facing in the direction that we are. A simple way to remember this is the right hand grip rule. You stick your thumb up, Your thumb points in the direction of the current, and your fingers wrap around in the direction in which the field goes around the wire. You can imagine that the wire is passing through your fingers. This must be done with the right hand. It can be done in any direction though.
So the formula for the strength of a magnetic field is equal to B is equal to mu I over 2 pi d. Mu is the permeability constant. Which is equal to 4 pi times 10 to the negative 7th. I is equal to current, and d is equal to diameter.
A cool application for our topic, which is applicable to medical sciences, is called remote magnetic navigation. It is a powerful technique for controlling devices inside the human body. A magnetic field produced by current-carrying wires can be applied to medical instruments from an external source intended for surgical navigation. It enables the locomotion of tethered and untethered objects without the need for a local power supply. By doing this, short distances are constantly being controlled from a coil-based field generator in order to determine exactly where and how the instrument is going inside the patient's body. Remote magnetic navigation allows for the precise movement of conductive objects inside a patient's body without the need for invasive procedures. Let's quickly see how remote magnetic navigation is applicable to real-life medical scenarios. Let's say in the United Kingdom, two English guys at a pub get into a bar fight, and one guy without a mustache throws a bottle of booze to another guy with a mustache. Unfortunately, a shard from the bottle is now caught in the guy with the mustache's arm, resulting in both ruptured tissue and possible nerve damage. Traditionally, such a protocol would require an invasive procedure where the surgeon would have to open up the arm and stitch up both the ruptured tissue underneath the skin and the ruptured tissue above the skin. However, with the introduction of remote magnetic navigation, the patient's arm can simply be placed in a room with coil-based generators which have the ability to apply a magnetic force on any conductive element in the room. The generator's ability to do this allows metallic elements such as small shards and screws to be controlled differently as the current in the generators is altered. In this case, the doctors would have to implement a small metallic and conductive screw on the outside of the arm and essentially control its path and force of movement by alternating which way the current flows in which coil-based generators around the room. This allows the screw to move around and basically tie up the ruptured tissue without the need of an invasive procedure, and also without the need of a local power supply.